12 years old is the perfect age to start coding. Old enough to grasp real programming concepts, young enough to build fluency before any bad habits take root. I'm Kazuki Tanaka, and over the past year, I've tested every major coding platform with actual 12-year-olds in my fabrication lab, watching them go from drag-and-drop blocks all the way to writing Python and building hardware projects. This is what actually works. You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear is researched and written by real people, verified for accuracy, but the voice you're hearing is AI generated. Just want to be upfront about that. If you've been listening to the show for a while, thank you for being here. I don't take it for granted. And if this is your first episode, welcome. We publish new episodes every Monday, Wednesday, and Friday, covering STEM toys, learning tools, coding platforms, robotics kits, all kinds of hands-on learning resources. Today we're talking about the best coding platforms for 12-year-olds. Let's jump in. Let's talk about Scratch 3.0 first. It's still the gold standard for learning how to think like a programmer. Developed at MIT Media Lab, Scratch teaches all the core concepts, loops, conditionals, variables, custom functions through a drag-and-drop interface that completely eliminates syntax frustration. Check the show notes for a link to the current price on the official Scratch coding cards, which provide great offline reinforcement. Here's what you need to know about running it. Scratch works in any browser on Windows, Mac, Chrome OS, even tablets. It's completely free, no subscriptions ever. Your project's saved to the cloud, and there's an optional offline editor you can download that's only 75 megabytes. You do need internet to access the sprite library and share projects with the community, but otherwise it runs on whatever device you've got. After about 30 to 40 hours, expect your kid to understand algorithm design, debugging workflows, sprite animation, coordinate geometry, and basic game physics. The platform even extends into hardware control through add-ons for Microbit and Lego Robotics. Our guide on teaching Python and block coding using Lego Robotics platforms covers those integration strategies in detail. Now, Scratch itself isn't used professionally, but here's the thing. The conceptual foundation it builds is identical to what professional programmers use. Event handlers, state management, modular code design, that all transfers directly to JavaScript, Python, C++. I've watched dozens of kids move from Scratch to text-based languages in 3 to 6 months once they nail these fundamentals. The downside shows up around hour 50 or 60. The visual interface starts to feel limiting when projects get complex. Kids working on programs with 200-plus blocks complain about scrolling through massive scripts. There's no autocomplete, no code refactoring tools. Scratch is a stepping stone, not a destination, and that's fine. Moving on to Python, this language deserves its reputation as the best option for 12-year-olds transitioning to text-based programming. I recommend Replit for online work or Thonny for offline environments. Both eliminate the installation headaches that kill momentum before it even starts. Replit runs entirely in your browser and needs at least 600 megabytes of RAM. The free tier gives you unlimited public projects. The paid hacker plan is $7 a month and adds private repos plus always-on projects. Thonny is a 20 megabyte download for Windows, Mac, or Linux. It includes Python 3.11 and requires zero configuration. Both support libraries like Pygame, Turtle Graphics, and GPIO for Raspberry Pi hardware. The first 20 hours focus on variables, data types, functions, and basic input-output. Hours 20 through 60 introduce object-oriented programming, file handling, and third-party libraries. By hour 100, capable students are building web scrapers, data visualizers, Discord bots, actual tools they'll use in their daily lives. Python powers machine learning frameworks like TensorFlow and PyTorch. It runs scientific computing through NumPy and Pandas. It handles web development with Django and Flask. It automates tasks across every industry you can name. It's the closest thing we have to a universal professional language. Our guide on building your first machine learning model with kids covers AI-specific applications. The friction point is error messages. They're cryptic for beginners. When Python spits out indentation error, unindent does not match any outer indentation level, that means absolutely nothing to a 12-year-old until they've debugged it 5 times. And compared to Scratch, there's no visual feedback. That requires stronger self-motivation. Next up, the Arduino IDE and hardware programming. Check the show notes for a link to the current price on the Arduino Starter Kit. Pairing that kit with Arduino IDE 2.0 teaches embedded systems programming through immediate physical feedback. LEDs light up, servos move, sensors respond. It makes abstract programming concepts tangible. The IDE is free, about 250 megabytes to download for Windows, Mac, or Linux. You need a USB connection to the Arduino board. I recommend the Uno R3 or Nano for beginners. It runs on 5 volts at 40 milliamps via USB or a 7 to 12 volt DC barrel jack. The expandability is exceptional. Hundreds of compatible sensors, shields, and actuators are available. After you download the initial libraries, it works fully offline. First projects, hours 1 through 15, cover digital input-output, analog reading, PWM control, and serial communication. Hours 15 to 40 introduce state machines, timing without delays, and sensor fusion. By hour 60, students are building autonomous robots, environmental monitors, home automation prototypes. Our article comparing Arduino versus Raspberry Pi for 12-year-olds explains the platform differences in depth. Arduino teaches C++, the language of real-time systems, robotics, aerospace, automotive engineering. The same pin control concepts apply to industrial PLCs and embedded Linux systems. I've seen students go from Arduino to contributing to FRC robotics teams within a year. The challenge is that hardware debugging adds complexity. Is it a code problem, a wiring issue, a dead component? Students need patience and systematic troubleshooting skills, and the kit requires a $50 to $80 initial investment, plus consumables like wires, resistors, LEDs that need replacement. Now let's talk about the microbit. Check the show notes for a link to the current price on the BBC Microbit Go bundle. Using that with Microsoft MakeCode strikes a brilliant balance between visual and text programming. The platform offers side-by-side block and JavaScript views, so students see code translation in real time. The browser-based editor works on all platforms and is 100% offline capable through Windows, Mac, Android, or iOS apps. The microbit board runs on 2 AAA batteries with about 80 hours of life or USB power. It includes an accelerometer, compass, 5x5 LED matrix, 2 buttons, and a 25-pin edge connector. Hundreds of accessories expanded. No subscription required. First 10 hours cover basic input-output, animation, and game logic. Hours 10 to 30 introduce radio communication, that's peer-to-peer networking, sensor data collection, and servo control. By hour 50, students build wireless weather stations, step counters, data loggers, real citizen science tools. Our Microbit Citizen Science Kits guide covers those projects. The JavaScript underneath prepares students for web development, while the hardware interaction teaches IoT concepts used in smart buildings, agricultural tech, industrial monitoring. The limitation is that 5x5 LED matrix. It's pretty restrictive for complex displays. Students outgrow the microbit faster than Arduino because the board's built-in capabilities are finite. You hit the ceiling around hour 60 to 80 without purchasing expansion boards that approach Arduino prices anyway. Code.org's CS Discoveries course is next. This isn't just a platform, it's a complete middle school curriculum covering web development, animation, data science, and physical computing. I've used it with homeschool co-ops where parents have zero tech background.
It's entirely browser-based, free, works on Chromebooks, tablets, desktops, cloud-based progress tracking, optional teacher accounts with class management tools. It includes built-in assessment tools and standards alignment documentation. Big caveat, it requires consistent internet access. The offline story is weak. The full course spans 90 to 120 hours across an academic year. Unit 1 and 2 cover problem solving and web fundamentals, HTML and CSS. Unit 3 introduces Game Lab, which is JavaScript-based animation. Unit 4 explores data visualization. Unit 5 integrates microbit or circuit playground. Students complete portfolio projects demonstrating computational thinking, collaboration, debugging, persistence. The web development units teach HTML, CSS, JavaScript. Those are actual job skills. The data science unit introduces concepts used in analytics, business intelligence, and research. It's less about specific tools and more about computational practices that transfer everywhere.
The challenge is pacing. It assumes classroom structure. Self-directed learners sometimes struggle with motivation through the slower explanatory videos, and the JavaScript environment is sandboxed. You can't install libraries or use external APIs, which limits advanced students. Roblox Studio is something different. Check the show notes for a link to the current price on the Roblox coding book for kids, which supplements Roblox Studio. This is where 12-year-olds build actual games played by millions of people. The Lua scripting language is approachable but powerful. Professional game studios use Lua in production engines. Roblox Studio is a 500-megabyte download for Windows or Mac, free with a Roblox account. Publishing games is free. Monetization is possible through in-game purchases, though Roblox takes a 30% commission. You need a decent GPU. Integrated graphics struggle with complex scenes. Cloud saving is included, but offline editing is limited. Testing requires an internet connection to Roblox servers. Hours 1 through 20 focus on 3D workspace navigation, object properties, basic scripting, variables, events, functions. Hours 20 to 60 introduce data store systems, GUI design, game mechanics like physics, collision detection, animation. By hour 100, capable students build multiplayer games with leaderboards, in-game economies, custom tools. Lua is used in game engines, embedded systems, application scripting. More importantly, Roblox Studio teaches 3D coordinate systems, physics simulation, client-server architecture, user experience design, all game development fundamentals. The platform itself has launched teenage developers to six-figure earnings. The friction is that it's a social platform. Kids interact with strangers. Inappropriate content exists despite filtering. Parents need to enable account restrictions, and the monetization angle creates unhealthy obsession for some kids who prioritize making money over learning fundamentals. The P5.js web editor teaches JavaScript through visual art and animation, perfect for visually motivated learners who found Scratch too childish but text programming too abstract. It's based on processing and used in art schools and creative coding courses worldwide. The browser-based editor at editor.p5.js.org is completely free, no sign-up required, though optional accounts let you save projects. Works on any device with a modern browser. Fully offline capable if you download the p5.js library and use local HTML files. Zero power requirements beyond your computer. First 15 hours cover coordinate systems, shape drawing, color theory, animation loops. Hours 15 to 40 introduce interactivity, mouse and keyboard input, trigonometry for motion, array manipulation for particle systems. By hour 60, students create generative art, data visualizations, interactive installations that run in any web browser. P5.js teaches JavaScript, the web's native language, plus concepts used in data visualization like D3.js, creative agencies, interactive media design. The mathematical thinking, vectors, transformations, probability distributions, applies to game development and simulation work. The downside is it's purely output-focused, no built-in way to save user data, connect to databases, or build full applications.
Students who want to make practical apps, to-do lists, chat programs, hit limitations quickly. The creative coding focused appeals to artistic kids but leaves engineering-minded students wanting more. Tinkercad Circuits by Autodesk lets students prototype Arduino projects in simulation before touching real hardware. I use this in my lab to reduce wasted components and shorten debugging cycles during physical builds. It's browser-based, free with an Autodesk account, runs on Chromebooks, tablets, desktops, includes an Arduino Uno simulator, breadboard components, code editor with block and text modes. Cloud-dependent though, no offline mode. Simulates power requirements but uses zero actual electricity. Hours 1 through 10 cover circuit basics, series versus parallel, current flow, component symbols. Hours 10 to 30 introduce Arduino programming with immediate visual feedback, LEDs light in real time, servo arms move on screen. By hour 40, students design multi-sensor systems, test code logic, generate parts lists for physical builds. Pairs perfectly with our guide on teaching kids 3D design skills with Tinkercad and Fusion 360. Circuit simulation is standard practice in electrical engineering. Professionals use SPICE simulators that work on identical principles. The workflow, design, simulate, debug, build, mirrors industry practice. The 3D design integration teaches CAD basics used in mechanical engineering. The problem is, simulation doesn't capture real-world issues, flaky breadboard connections, power supply noise, component tolerance variations. Students sometimes assume code that works in simulation will work perfectly in hardware, which leads to frustration during physical builds. Tinker offers one of the most polished learning progressions out there, with over 3,000 guided activities spanning block coding through Python and JavaScript. The production quality rivals commercial games. It's web-based and has mobile apps for iOS and Android, works on all devices. Requires a subscription. The home plan typically runs around $20 a month or $120 a year, though prices vary by promotion. Includes a parent dashboard with progress tracking. Internet dependent for course content, though some activities can be downloaded for offline work.
The curriculum spans 150+ hours with clear milestones. Early courses cover loops, conditionals, debugging. Intermediate courses introduce variables, functions, data structures. Advanced tracks dive into Python web development, JavaScript game programming, even drone coding simulation. The structured approach works brilliantly for sequential learners. Later courses teach industry-relevant frameworks, Python Django, JavaScript Canvas API. The progression intentionally builds skills that transfer to AP computer science coursework and tech internships. The subscription cost is real, $120 to $180 a year depending on sales. Unlike free platforms, you're locked in if your kid loses interest, and the high production value sometimes feels gamified in ways that obscure actual learning. Kids complete activities for badges without understanding underlying concepts. Compare your options against our guide on free programming kits for different skill levels before committing to paid subscriptions. Finally, the Raspberry Pi. Check the show notes for a link to the current price on the CanaKit Raspberry Pi 4 Starter Kit. This transforms a credit card-sized computer into a complete coding laboratory. Running Linux, it teaches operating system concepts while supporting every language from Scratch to C++. You want a Raspberry Pi 4 with at least 4 GB of RAM. The kit includes a power supply, 5 volts at 3 amps via USB-C, pulls 15 watts, micro SD card with at least 32 GB, mouse, keyboard, HDMI cable. It runs Raspberry Pi OS, which is Debian Linux, comes with Python, Scratch, Thonny, Arduino IDE, LibreOffice pre-installed, fully offline capable after initial setup, 40-pin GPIO header for hardware projects, 4 USB ports, dual micro HDMI outputs. First 10 hours cover Linux navigation, file systems, basic troubleshooting. Hours 10 to 40 focus on Python programming with GPIO control, blinking LEDs, reading sensors, controlling motors. Hours 40 to 80 introduce networking projects like web servers, network scanners, media centers. By hour 100, students build smart home hubs, retro gaming systems, cluster computing demonstrations, projects that fill a home STEM lab, as described in our Home STEM Lab setup checklist. Linux skills are foundational for server administration, cloud computing, cybersecurity, DevOps careers. GPIO programming teaches embedded Linux used in industrial systems and automotive computing. Python plus hardware integration is exactly what IoT engineers do professionally. The friction is setup requires more technical confidence than plug-and-play platforms, formatting SD cards, connecting peripherals, troubleshooting boot issues. The initial cost is $80 to $120, higher than most beginner options, and updates occasionally break things. I've seen keyboard mapping revert randomly after OS updates, requiring command line troubleshooting beyond typical 12-year-old patience.
So how did I make these picks? I tested these platforms across 3 criteria: technical capability progression, industry relevance, and total cost of ownership. Each platform was evaluated with 12-year-olds in my fabrication lab over 6-month periods, tracking engagement, frustration points, and skill transfer. Technical capability progression measures how platforms scaffold learning from absolute beginner to meaningful intermediate competency. I disqualified platforms that hit skill ceilings before 60 hours of engagement. Every platform here provides clear paths to advanced concepts: object-oriented programming, hardware integration, web development fundamentals. Industry relevance matters because we're building career-ready skills, not just passing time. I prioritized languages and tools used in actual professional environments: Python for data science, machine learning, automation; JavaScript for web development, C++ for embedded systems and game engines, Lua for game scripting. Platforms teaching proprietary languages with no career pathway were excluded. Total cost of ownership includes hardware, subscriptions, consumables, replacement parts over 12-month usage periods. Free platforms like Scratch and Code.org score exceptionally well. Hardware platforms like Arduino, Microbit, and Raspberry Pi require upfront investment but no recurring fees. Subscription services like Tinker were evaluated against the value delivered versus free alternatives. Where paid platforms made the list, they provide structured curriculum worth the investment for specific learning styles. I also tracked expandability, whether platforms support progression beyond their core scope. Arduino and Raspberry Pi excel here with massive accessory ecosystems. Scratch integrates with robotics kits, as explained in our LEGO Robotics Programming Guide. Platforms that dead-end without expansion options were deprioritized. Let's hit some common questions. What's the best coding platform for 12-year-olds with no prior experience? Scratch 3.0 is the best starting platform because it teaches core programming concepts without syntax frustration, it's completely free with no subscriptions, and MIT provides exceptional documentation plus an active community for troubleshooting. Plan to spend 40 to 60 hours here before transitioning to text-based languages like Python through platforms like Replit or Thonny. Our article on designing a STEM learning path for 12-year-olds outlines that progression.
Should 12-year-olds learn Python or JavaScript first? Python, because the syntax is cleaner, no semicolons or brackets cluttering code, the error messages are more readable, it's used across more career paths like machine learning, data science, automation, web backends, and it works seamlessly with hardware platforms like Raspberry Pi and Arduino when kids are ready to expand beyond screen-based programming. JavaScript makes sense as a second language after Python fundamentals are solid, particularly if the child shows interest in web development or game programming. Our Robotics Programming Languages comparison discusses this more. Do coding platforms for 12-year-olds require expensive subscriptions? Most of the best platforms are completely free. Scratch, Python via Replit or Thonny, Arduino IDE, Microbit MakeCode, Code.org, P5.js web editor cost nothing for software.
Hardware platforms like Arduino, typically around $50 to $80 for starter kits, Microbit at around $60 to $80 for the Go bundle, and Raspberry Pi at around $80 to $120 for complete kits, require one-time equipment purchases with no recurring fees. Subscription platforms like Tinker, typically around $120 to $180 a year, provide structured curriculum but aren't necessary for capable self-directed learners or families willing to piece together free tutorials. How long until a 12-year-old can build real projects after starting coding? With consistent practice of 3 to 5 hours per week, most 12-year-olds build their first meaningful projects within 8 to 12 weeks, regardless of platform. Scratch users create working games with scoring, levels, custom sprites. Python programmers build text-based games, simple Discord bots, data visualizers. Arduino learners construct automated systems with sensors and servos. Roblox Studio users publish playable multiplayer games. The key milestone isn't time invested, but completing 25 to 40 hours of deliberate practice with progressively complex challenges, following structured learning paths like those described in our complete STEM learning path guide, rather than random tutorial jumping. Here's my final take. The best coding platforms for 12-year-olds aren't necessarily the flashiest or most expensive. They're the ones that match your child's learning style while building industry-relevant skills. Start with free options, Scratch, Python, Code.org, to identify interests before investing in hardware platforms or subscriptions. I've watched the most significant learning happen when kids build projects they actually care about. Automation tools for games they play, hardware that solves real problems in their rooms, creative coding that combines art with programming. Choose platforms that enable those intrinsic motivations rather than impose external curriculum.
Every platform here provides clear capability milestones and progression paths toward professional tools. The biggest risk isn't picking the wrong platform, it's picking nothing and letting another year pass without building these foundational skills. Start this week with whatever option removes the most friction from your specific situation.
That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. New episodes drop every Monday, Wednesday, and Friday, so there's always something new coming your way. If you found this episode helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It actually makes a huge difference. It's how other people who need this kind of information end up finding the show. And make sure you're subscribed or following the podcast so you get notified the second a new episode goes live. See you next time.